Hello everyone and welcome to 10th lecture of Global Navigation Satellite Systems and Applications. And in this discussion we are going to discuss a Japanese system which is called Quasi-Zenith Satellite System for Navigation, that is QZSS. And it has been developed by a Japanese aerospace exploration agency, like in US we are having NASA, in India we are having ISRO. So this JAXA agency of Japan has developed this regional system. So in Japanese it is called the Michibiki, and that means to guide, to show the way. And this is regional navigation system is there, and this is regional navigation satellite system. It is not global, and Japan is being a very small country in sense of geographic area, and they wanted to develop for their own purposes. But the interesting part from navigation systems point of view, we are also sometimes getting signals from QZSS in India as well, but not from many satellites, because as we will see that the constellation is different. But anyway, from at least maybe from 1 or 2 satellites, if our receivers are capable of receiving those number of channels, then we are also getting QZSS signals in our receivers. So at the beginning the system was basically developed by the Advanced Space Business Corporation team of JAXA, and in 2007 the work taken over by the JAXA together, and the Satellite Positioning Research and Application Center of JAXA is now in full command. As you can see that this orbit is completely different. That is why it is a quasi kind of arrangement. This QZSS service area covers East Asia, Oceania region, and its platform is multi-constellation GNSS system. So this QZSS system is not required to work in a standalone mode, but it depends. It is not completely independent, but it together with data from other GNSS satellites. So it is a kind of augmentation systems, and this augmentation is mainly focused for Japan. It is not exactly as SBAS, but of course because it is not independent systems, it depends on other GNSS systems, which we will see very soon. That there are 3 satellites placed in periodic highly elliptical orbit, which we can see here, that there are these 3 orbits are there, and 3 satellites, 1 satellite, another one, and third one, and a 4th is in a geostationary, so that it keep looking, or it is synchronized with the speed of Earth, and the satellite will always keep focusing over Japan. So this is what we see, that one satellite is here, another one is here, it is also here, and the main focus, it is not completely circular, and that is why it is called Quasi-Zenith satellite system. 3 orbital planes, as you can see here, and there are 3 satellites, 40-degree inclination angle, and the altitude is relatively very high as compared to GPS or GLONASS or other systems are there. So this is how the constellation is there, and for this highly elliptical orbit of QZSS, the perigee which you see here, the perigee is 32,000 kilometer, where you will have the fastest velocity, and that is the closest point to the Earth, and apogee is the farthest point of the Earth. So this is basically apogee is there, and this altitude or the distance of apogee is about 40,000 kilometer, and all over them will pass over the same ground track, and that is why in here what you were seeing, that orbit is not a regular one. So it's a different kind of orbit which you are seeing here. It's a not independent system. It will be using other GNSS signals along with QZSS to improve the positional accuracy basically over the Japan and maybe in neighboring countries. And QZSS is designed so that at least one satellite out of 3 satellites exists near zenith over Japan. And not many satellites have been intended because other satellite signals will be available from other GNSS systems which are global. And so in this orbit each satellite will appear almost overhead most of the time. And this is the same advantage is being taken as in case of IRR systems, that most of these satellites are overhead over us because of geostationary in nature, and more than 12 hours a day with an elevation of 70 degree. So that is the biggest advantage, that these, like it will be an overhead, few will be here in other in inclined position, but nonetheless they will be providing good signals for a geographically small country. So this gives rise to the term quasi-zenith, for which the system is named. And as you can see here in this animation, that how from a location in Japan, how these access to these satellites are available. As you can see that all 3 satellites are moving and in their designed orbit, and this is how they will be getting at least one satellite will always be there, and another one is the of course geostationary, which is all the time focusing, and signals from other GNSS system will allow to estimate accurate position for within the Japan. And as number of satellites 3, number of orbits 3, as you have seen, the inclination is 43 degree, and eccentricity is 0.075, major semi-axis is 42,164, and apogee orbital period is 1 side real day, and the perigee distance is 39,002 kilometer, apogee distance is 45,326 kilometer, and some other parameters yet to be defined, that is RAN. Argument of perigee is 270 degree, and central longitude ground trace at 15 degree. So this design life of quasi zenith satellite or QZ system for each satellite is 10 years, and this is almost true in most of the satellites which are in very far deep in space, much more away from the earth. We have already discussed this point, that if a satellite is very close to the earth, low earth orbit, the life of such satellite would be less. When if satellite very deep in space, generally life of these satellites may go up to 10 years or sometimes even 15 years. And first satellite of this Michibiki or QZSS was launched on 11th September 2010 and injected into the quasi-zenith orbit on 27th September, and that is 2010. So these are the frequencies which are being used by QZSS. L1 frequency, this is coarse acquisition, and L1C and L2C, L5 and L1 CEF and LEX. And one by one we will see that L1 CA and C, that is 1575.42 megahertz, which is complete compatibility and interoperability with the existing and future modernized GPS signals, because it will be using the signals from other GNSS systems, for example GPS. So the same frequencies have also been incorporated, so that in receivers these things are there. Then for L2, L5, the differential correction, data integrity flag and ionospheric corrections will also be done through these frequencies. Almanac and health of other GNSS space vehicles will also be coming through these frequencies. And L1 CEF is the compatibility with GPS and SBAS. SBAS, that is a satellite based augmentation system, which is now becoming a very popular, and almost every country is trying to have their own geostationary satellite, so that they can have satellite based augmentation. And what the advantage of course we will be having a full discussion, one lecture on this SBAS, but at this stage the advantage of SBAS, because these differential corrections can come through this SBAS, because this SBAS, which is in geostationary orbit, and the signals from SBAS will always be available for that country which has planned or launched these SBAS. So India is also having this SBAS our system. Many countries are have already have their own SBAS or planning to have their SBAS system. And this LEX, that is the experimental signal with higher data rate message, 2 kilobytes per second, compatibility and interoperability with Galileo E6 signals are there. So as mentioned already, the QZSS is not completely independent system. Only 4 satellites, 3 in this quasi-zenith orbit, 1 is in geostationary. Rest of these things are being managed from other GNSS system. So that in probably they are not intending from that kind of military operations or other things, but for civilian these number of satellites and available accuracy hopefully will be sufficient. And of course they are not looking in that sense a complete independence or independent system of their own, but using their other GNSS systems which are already available. Now as you can see that these ground track and control stations, how they are spread. So they are having these stations, ground stations, which are in these red dots, which are all spread all over the world, and of course in Japan or near Japan. So ground station basically constantly monitor the GPS signals. Sometimes we also call them as monitoring stations for generation of correction messages, and then they send these QZSS satellites for immediate rebroadcast to all augmentation enabled receivers in coverage area with an overall turnaround of under 5 seconds. So very quickly the corrections are sent to the satellites from these ground monitoring stations, and then these are also passed to the user or to the receiver, where signals are being used for position estimation or for recording. And these augmentation messages, the purpose here is to improve the accuracy, include information such as differential correction, that is the error which is being recorded and communicated to the receiver ultimately, so that you get the more accurate position. As if there are some errors in the satellite orbit, these monitoring stations keep monitoring, and then they transmit. Ionospheric delay, that is always incorporated in the signals, and other essential parameters may also be sent through these monitoring stations to master control stations or other uplinking stations. So the benefits of this QZSS, there are many, that there are mobile mapping systems which can utilize convoy truck systems and for fleet management. Of course, this is the future. This is the automated driving which is coming now, which is going to be completely based on GNSS systems. Some prototype vehicles have already been developed. In the end of this course, we will be of course discussing those things as well. Then the smart driving support system and maybe smart intersections, and all these systems are also focusing on disaster prevention, and in case of emergencies, availability of signals and distress signals also. And then efficiency of infrastructure maintenance, for that purpose also tunnel surface management. If there are like there are large civil structures, maybe a reservoir, a dam, maybe a tunnel. If there are any deformations are happening, then if accurately the data is measured on regular basis, then such things can be estimated, and it is being done. Then landslide protection also, these signals can be used, railway management, area surveillance, high precision navigation, road pricing, information control centers, all kinds of applications will be there using these QZ signals. And this is one comparative chart of so far the systems which we have, GNSS systems, different GNSS systems which we have discussed, starting here the GPS which is of United States. Then we have also discussed the GLONASS of Russia, and then we have also discussed the Baidu China system, and then we have also discussed the NAVIC or IRNSS, which is our India system, and in this particular lecture we have also discussed the Japanese one. As you can see that Chinese one, though originally it started regional, but it is now global. It is already global. At least in India we are getting good quality signals from Baidu. Galileo is ultimately intended for global operations. GLONASS and GPS, anyway they were designed for global. Indian system is regional, and this QZSS, that is Japanese system, is also regional. The coding system, some are using CDMA, some are using like GLONASS is using FDMA, the rest of the systems are using CDMA. And we have also discussed about the orbital altitude, that is the distance of these satellites or constellation from the Earth. So in that this GLONASS is are the closest satellites relatively, and whereas the NAVIC are at the farthest, because we are also using geostationary orbits as well. So they are very far in space or very deep in space, and the period, that means the how they complete one cycle or one orbit of the Earth. So this Baidu 12 hours, our Indian systems is also depending on different satellites, and then 11 hours GPS and so on so forth. Revolution per sidereal, and so 17.9 out of and 17.10, then 17.8, 2, and this information is not available for it. And now number of satellites, as you know that in case of GPS which we started 31, in case of GLONASS 28 total, in case of Galileo 24, and 6 are in spares. So basically the 30 satellites, and in case of Baidu 5 geostationary orbits, 30 medium earth orbits, and in case of Indian system 3 geostationary orbit, 5 geosynchronous orbit, and QZ also, as you have seen that 3 in the quasi-zenith orbit and 1 in geostationary orbit. And these are the frequencies which are being used by different navigation systems, and this is the status is that Baidu is working, Galileo is working, though we do not get signals in India, but it is known that it is working. GLONASS is working, and GPS is, of course, it is working. GLONASS signals also we receive in India, so we know that it is working. And IRNSS, as mentioned when we have kept our focus on the discussion of IRNSS, that only for military purposes it is open, but for civilian standard positioning services that is not available yet to civilians, but hopefully very soon these things would also be available for normal people. And the most important part is the precision without using SBUS. So there are for standard services or precision services. In case of standard services, Baidu 10 meter. In case of Galileo, it is just 1 meter, so it's highly accurate relatively. In case of GLONASS, 4 to 7, 4.5 to 7.4 meter. In case of GPS, of course, without differential GPS, or WAAS, that is a wide area augmentation system. And then India for public will be having, not yet, that is going to be 10 meter, but encrypted for military purposes it is going to be 0.1 meter. And QZSS, we get 1 or 2 satellite, mainly 1 satellite signals from QZSS, and that is 1 meter for public, and of course for special services or encrypted services for which one has to pay is 0.1 meter. So, in this gives a comparative study or comparative chart of all the navigation systems which so far we have discussed belonging to different countries or union, like European Union in case of Galileo. So, this brings to the end of this discussion on QZSS, which is Japanese system, and this also completes the all GNSS systems so far which have been developed by different countries, and in future we will be discussing the differential GPS, SBAS and other things. As usual, I am leaving again with a cartoon to enjoy. Thank you very much.